In this lesson, we're looking at exponential relations. We've seen in previous lesson that an exponential relation is one that has a certain shape to it. If we graph it, it's sort of got that sloping look. We saw that the tables have a common ratio instead of a common difference. And we're going to carry on and we're going to look at the equation right now. So you can recognize an exponential relationship because the variable, pardon me, is always the exponent. So in this case, y equals b to the x, where b is just some, it can be any letter, any number. So it's always going to be in this form, okay? So for example, an exponential relation might be y equals 2 to the x. That has x, the variable, as the exponent. Compare that to a quadratic, all right? So this is exponential. Compare that to quadratic, which looks like y equals x squared. And here's the variable in this case. So people confuse these sometimes, but really it's very simple to see the difference. The exponential equation has the x as your exponent. B can be any number. The base, think of b for base, can be any number other than 1. And the reason why it can't equal 1 is because 1 to any exponent still equals 1. Because think about, say, 1 squared. That means 1 times 1. 1 times itself twice. Still 1. 1 to the 3, 1 times 1, still 1. So it doesn't matter what exponent you put on 1, you're always going to get 1. Whereas if you have any other base, like 2, 3, 4, 10, a million, whatever, it'll grow in an exponential way. Same with if it's a number between 0 and 1, it'll decay in an exponential way. We can't have negative bases either, okay? So b can be any number other than 1. Let's say, or a negative number. Pardon my writing, not very neat. That says, or a negative number. So create a table of values and graph each relation. We'll do the first example. Okay, so x, so the first one is y equals 2 to the x, as we already looked at, right? Well, remember, when we want to make a table of values, we choose our x values, and then we just see what the y values are that come out of them by sticking the x values into the equation and then getting the y values. So if I stick negative 2 into the equation 2 to the x, I'll have 2 to the negative 2. And we saw previously that negative exponents mean 1 over something. It means 1 over 2 to the power, the positive 2. But 2 to the 2 is just 4. So 2 to the negative 2 is 1/4. And then 2 to the negative 1 becomes 1 over 2 to the positive 1, which is just 1/2. 2 to the 0, as we already know, anything to the exponent 0 equals 1. And 2 to the 1 equals 2. And 2 to the 2 equals 4. 2 to the 3 equals 8. So these are our y values that go along in each of our ordered pairs here. So we got our x values, we've got our y values. We can plot them. So the first one, negative 2 and 1/4, so negative 2 on the x, 1/4 on the y, that's about there. The next one, so I've moved on to this one, is negative 1x and 1/2 for y. And then move on to the next one, and we've got 0 and 1, which would be here. And then move on to the next one, we've got 1, 2. And then move on to the next one, we've got 2, 4. And then we've got 3, 8. And then we connect these with a smooth curve, at least to the best of our ability, which for me is always a little bit shaky, but there you go. Could have been a bit smoother here. Try to smooth that out a little. There it is. There's my graph. All right, let's do the same thing for B part. We got a base of 1/2. So let's try 1/2 to the -3. We've seen already that negative exponents on fractions are just going to flip them upside down. So that's the same as 2 over 1, flip the base upside down to the +3. And then we saw, I'm going to have to sort of keep writing and filling in this space, or overfilling this space. I put this 3 on the top and the bottom. That's the same as 2 to the 3 over 1 to the 3. Well, 2 to the 3 equals 8. 1 to the 3 equals 1. Again, we're just multiplying the base by itself 3 times. 8 over 1 just equals 8. So all that works out to equal 8, and it makes perfect sense as long as you understand the different rules of exponents. So if I have 1/2 to the -2, it's the same thing. It's going to be 2 over 1 to the +2. So following that same pattern, we're going to end up with 4 over 1, or just 4. And then we're going to end up with 2 over 1 to the +1, which is just 2. And then we're going to have anything to the exponent 0 equals 1. Anything to the exponent 1 just equals itself. And then this last one, 1/2 to the +2. Again, that's going to be 1 to the 2 over 2 to the 2, which equals 1/4. So here's the different parts. Again, I got these y values that I'm going to stick in to the equation. And then once I crunch the numbers, it comes back out. So I have x values I stick in, and I crunch numbers, they come back out as y values. Together they make an ordered pair. And again, this is what I'm going to plot. I'm going to plot -3 and 8. Well, -3 and 8 is all the way over to the left and up at this point here. -2, 4 is here. -1, 2, 0, 1, 1, 1/2, and 2 and 1/4. So let's see if I can draw any kind of smooth curve through this. It's not my worst work. So there's that one, okay? So there's what the graph looks like. So describe the 2 exponential graphs you sketched above. I've already filled this in to save a bit of time. Both of them are smooth curves, almost horizontal at one end and almost vertical at the other end. Graph A is called growth because the base, which is the common ratio, is 2. In other words, it's a number bigger than 1. Let's add this in here. Greater than 1. Anything greater than 1 is going to be growth. It's going to go up to the right. Graph B is decay because the base is 1/2. In other words, the base is between 0 and 1. Remember, we can't have negative bases. So it goes down from, graph B goes down from left to right. Graph A goes up from left to right. Growth, decay. Anytime the base is greater than 1, there's growth. Anytime the base is between 0 and 1, there's decay. Base cannot be negative. Okay, recaps what we've already said. All right, let's create a table of values and graph each relation here. Well, the only difference between question 2a and question 1a is that they've added a 2 in front of the 2 to the x. In other words, they've added this. Y equals 2 to the x was 1a. So it just means that if I take all my answers from 1a and multiply them by 2, I'm going to get my new y values. In other words, when I had, I already know that 2 to the -2, 2 to the -2 equals 1/4. If I multiply that by 2, I'm going to get 1/2. 1/4 times 2 equals 1/2. So I can save myself a little bit of time and fill in this table here. So this one's going to equal 1/2, and if I go back to the next one down, if I multiply this by 2, a half times 2 equals 1. And if I multiply this by 2, I get 2, and this by 2, I get 4. So I'm just multiplying all these answers by 2 because of this 2 out front. So I get 1, 2, 4, 8, 16. And then we can plot it. And then 316 does not fit on the graph, so I won't worry about that one. I'll just know that it's going to shoot up quite far and look like that. Here, we've done the same thing. We're going to take all those answers from question 1a, but instead of multiplying it by 2 this time, we're going to multiply them by a half. Multiply them by a half. 0.5 is the same as a half. Multiplying by a half is the same as dividing by 2. So in other words, when x was -2 in this one, I got a y equals 1/4. Now I'm going to multiply that by a half, which is the same as dividing by 2. A quarter divided in half actually becomes an eighth. So now we're getting smaller numbers rather than bigger ones like I did in part A of example 2. So then we get an eighth, and then the next one was a half here. If I divide that in half, I get a quarter, and we start to see a pattern going on. The next one would have been 1, so I'll divide that in half, and I get a half. This one would have been 2, cut in half is 1. This is 4, cut in half is 2. This is 8, cut in half is 4. So again, we can plot these. Okay, and the graph looks like this. How do the two equations and graphs above differ from the equations and graphs of part A from example 1? That's what I was just comparing them to when I was coming up with my numbers. Well, the graph in example 1 had a y-intercept of 1. So in other words, we're going back to this one here. It had a y-intercept of 1. The y-intercept is where it crosses the y-axis. Y-intercept. Because anything to the exponent 0 equals 1. That makes sense. These graphs have y-intercepts that are equal to the a value of the equation below. By a value, they mean that number below, because that's our vertical stretch. So in other words, what I highlighted here is the a value. What I highlighted here is the a value for this one. So these are, you'll notice, are y, pardon me, our y-intercept for this one is this. It's 2. Our y-intercept for this one is a half. So we can always get our y-intercept by looking at the a value the way it's set up like that. All right, and I think that should be enough to get you going through the homework here. I mean, some of the questions are not directly related to the examples we just did. For question 1, all we're doing is recognizing from the graph whether something's linear, quadratic, or exponential. Remember, linear is a straight line, quadratic's a parabola, exponential's got that curve type look to it. So question 1 should be pretty easy. Question 2, how do these two graphs compare? You can make a table of values for each of these and then draw a sketch that way. But I think even before you do it, you should be able to predict the main difference between them by looking at the difference in their bases. Remember, go back to the rules for how different bases react. If we want to sketch each of these, well, we already did this one up above. If you look back at example 1b, I think we've got this one here. And then if we just multiply everything by 4, then we'll get a new value for that. Think of that as our vertical stretch. So all of these are going back to 1b and then just multiplying the values by what I've highlighted in yellow. Here's one where we fill in the example or fill in the values. Just use the equation, fill it in. Not a big deal. And then another word problem. So again, we're just tying things together for exponential.